Well, thank you very much for this introduction. It's a pleasure to give this presentation here for this audience. I'm afraid I have to do it in English. My Italian is a bit rusty. I might have chosen an AI application, though, to do a simultaneous translation from English into Italian, but I'm sorry. My name is Ronald Niemeyer, and I'm the Global Brand Manager of Biopharm, and I was asked to share some thoughts about the role of AI, artificial intelligence, in food safety and in food analysis. So I collected some of my thoughts, and a little disclaimer, these are my ideas and thoughts, and they do not necessarily coincide with the thoughts and ideas of my employer. And well, AI is the big buzzword, of course, lately, isn't it? The last couple of years, AI everywhere. And funny thing is that AI is actually not so new. I mean, the first publications around what we know now as artificial intelligence were from 1950. Alan Turing, when he published this publication and described actually what artificial intelligence by computers could be. And the name artificial intelligence was actually given in 1955 at the Dartmouth conference by John McCarthy. And what was my first, let's say, time when I really realized about artificial intelligence was when Deep Blue, this chess computer, was able to beat Garry Kasparov in 1997 with a chess game. It was quite amazing at that time. And I learned later that chess is actually considered to be a relatively simple game, said the guy who doesn't understand a thing about chess, but the real challenges would be, for example, a game like Go. And it took the time until 2017 to develop a machine learning, or actually a deep learning system, that was able to beat the actual world champion in Go. So developments have taken some time to really get to the level where we know AI now, and you probably have some of these gadgets at home, Alexa, Siri, or you use ChatGPT on a regular basis. It actually means that AI is now, well, 75 years old. It's a celebration year, yay. And a little fun fact, the big breakthrough of AI was actually the result of the gamers, the gaming industry, because they used for these games actually the graphic card instead of the CPU. And that really ignited this revolution of AI that opened so much more possibilities. So gaming does have sometimes also a good benefit. A few words about definition. AI, well, that's basically any technology that enables computers and machines to simulate human learning, and machine learning is just a specific part of that. So it actually enables computers to, well, behave like how humans are learning, and how they come to conclusions, and how they make predictions and so on. Machine learning can train on relatively small data sets. It may require human intervention, not necessarily. And it makes relatively simple linear correlations. And as I said earlier, the chess computer, the Deep Blue, was based on machine learning. And the one that was able to beat the world champion in Go was actually based on deep learning. Deep learning is a more advanced form of machine learning. And it uses, for example, neural networks. And sometimes they're also considered a bit of a black box, actually, what is doing and what the system is doing. And we now see so many forms of deep learning tools, deep learning kinds of algorithms, like, for example, the CNNs, the convolutional neural networks, or, for example, the pre-trained transformers, like ChatGPT is one of them, or also for the generative art, like Midjourney and so on. There are different kind of models for different kind of applications. Just a little also the definition of some forms of learning. Supervised learning is when you train a system with data that have a fixed outcome. So the system actually learns from sample A has an outcome of this. But you can also choose for unsupervised learning. There's also a model, and it's particular used in, for example, deep learning tools. So how is AI now developing in the research and in, for example, particular towards food safety? And there are some couple papers published recently. There's one here in June 2025 that about the impact of artificial intelligence on research efficiency. And actually the predictions are that the impact of AI will be huge. It will open new dimensions of research, a new dimension of productivity, and it will actually complement the way we deal and the way we do research. And the second publication, which is from September in Food Control, about the role of artificial intelligence in the advancing of food safety. It's a bit optimistic what they say, that it probably could be the strategic path to zero contamination. I'm not sure if that will be really the case, but what they say is actually true. It's the combination we now have by using the Internet of Things, by using all kind of internet-based tools with artificial intelligence, with analytical results, that will enable us, for example, to really enhance the way we deal with food safety. And I think in the near future, this will really be the way to go. I gave a presentation about artificial intelligence and mycotoxins earlier this year in Salzburg on the World Mycotoxin Forum. And one of the speakers there also was Thomas Hartung. And he gave a great presentation about the status of AI in toxicology. And he showed also this slide, and this slide shows what they call the protocol for question and answers, where you check if you can find the answer to a problem on the internet, but it is formulated in that way that Google will not exactly help you with the answer. You have to think yourself. And they compared the performance of PhD students insights in a specialty, and typically they performed very well. About 80% of the questions were answered correctly, and compared it also to, for example, human PhDs when they solve a question outside the specialty. Now, of course, the results will be a little bit lower. It's about 30%, 40% of the results are correct. And if you look at the development of the pre-trained transformers, so like ChatGPT, these generative forms of AI, about a year ago, they were at the level of an untrained PhD students. 1 year later, they exceed, let's say, the PhD students in their own fields. So the artificial intelligence is able to act like human beings and to really be as intelligent at the speed which is really unknown so far. So yeah, this development is just about starting. AI is already a hot topic in food safety, I would say. If you look at some of the articles where they try to collect all the articles and publications in this field around food safety and AI, this was a study from 2023. They looked at almost 2,000 articles between 2012 and 2020. And there were different studies in there that looked, for example, towards the analysis of foods, or, for example, the freshness of meat, quality of cereals and nuts, mycotoxins, for example. They suggested that there are some interesting fields, for example, for agriculture production, like precision agriculture or predictive models. For mycotoxins, it's always a kind of a surprise. Do we have mycotoxins this year, and where do they occur? And a predictive model, for example, would be really great if you would have that. Food processing, personal nutrition, and a lot of developments going on. Actually, these predictive models for mycotoxins. Mycotoxins are those toxins formed by molds in the field that are harmful for both the animals as well as for people. There are some models already published some years ago. For example, here is a machine learning on a model described for aflatoxin and fumonisin, which it was working in Serbia, and it could actually predict pretty well what the aflatoxin contamination would be based on weather data, based on field data. Also a study here from Italy in maize, which worked quite well. So for some mycotoxins, there are already some good working predictive models. This is one from the Netherlands, where they collected over 11 years data from, for example, the weather, crop data, flowering data, etc., and developed a machine learning model for that. And that model was able to predict pretty accurately the mycotoxin contamination of wheat at 3 levels in about a 25 to 25 kilometers grid. The problem is that it's still a relatively low resolution. Because if we have here some data from Trilogy, that's one of our daughter companies, they're actually a laboratory, and they saw that you can actually find sometimes mycotoxin differences in, well, let's say fields about 1 mile to 1 mile, also 1.26 kilometers to 1.6 kilometers. So this 25 is still a very, well, low resolution. And you actually can see quite big difference there. Aflatoxin on one part of the field and fumonisin in the other part of the field, just depending on the microclimate. So the actual models we have here are probably not good enough yet. And this is just an example. 2 fields very closely to each other. In one field, the planting date was May 15, and they got about 4 ppm fumonisin there. The next field, quite close. So we should have probably almost the same climate, but the planting date difference already gave a bigger production of fumonisin in this field. And if you want to make a really good predictive model, you should take this kind of changes also in your model. The current models we have with the machine learning are probably not good enough yet. And at Trilogy, we developed a model that's actually taking into account also these variations within the field, for example. And much more looks into the let's say, weather data, so it is a more actual prediction. We just recently launched this model, and well, it will be using more and more the data which are collected over the course of time to make a more accurate prediction model there. Another application is that AI is, for example, also used to actually say what the content is, for example, of Fusarium head blight in this case on kernels. And for a very basic method, they just use the kernels, put it on a flatbed scanner, used a deep learning model behind it. And this model was actually able to give a very good prediction which kernels were infected with Fusarium head blight and which not, about a 99% accuracy there. So it's another example of, in this case, where AI is supporting the analytical method, a very basic method, just a flatbed scanner. And if you look at, for example, the AOAC validated method, there is already a hyperspectral imaging method using AI approved for example, aflatoxin and other mycotoxins in corn and wheat. So there is some progress already made there. Now, how does this machine learning work? And this is based on a publication by Alan English. It's really a great presentation about the use of AI in the field of mycotoxins. And how it all starts with data. You need really good amounts and a real good amount of quality data. And you select those data and make them, prepare the data a little bit and select them into training data, validation data, and test data. Now, these training data are used, of course, to use this model, and they can have an outcome. So then they are used in, let's say, a supervised model, or they can be without the outcome, and the system learns from itself to identify patterns. And then you have a unsupervised model. The data are, the model is validated by using the validation data and then fine-tuned. And in the end, it's tested with the actual testing data. And it's always based, of course, on, let's say, that you have a good set of high quality data, because otherwise, the system will train itself on low quality data. Deep learning models they train themselves on certain features, which is of course a great tool, but it does have some disadvantages. And you have to really keep them in mind if you're using this kind of model and developing this kind of models. Neural networks are typically black boxes. It does something, but we have no clue what it does, but it seems to work. It's very difficult to understand how these predictions were made. Actually, if you were using, I'll come back to that later, an explainable AI, which is open and which shows how the decisions are made, is much more useful. But if you have these black box models, it is difficult. It's also difficult to quantify the measurement uncertainty. We don't know how it measures. Well, we see the results, but it might be very difficult if you do a proper validation to quantify measurement uncertainty. There's also a risk of what we call overfitting. If during the training, it might start actually to analyze the noise instead of the signal. That's also something you have to be aware of, that it is without the proper regulation, you might have a problem there. And yes, you can use, of course, the GPUs, not the CPU, but still, these deep learning models, they use enormous amount of computational power. You really need a strong computer to do this kind of calculations. So the availability of sufficient and diverse data is really crucial. If you use data from one lab, from one source, there might be a bias in the results you are getting. It would be really great if you can select data from different sources to have a really good working model there. In general, AI as such will of course not be able to measure, that's clear, but it can support the existing methods that are out there. For example, all those measurement methods that generate huge data sets, like NIR, for example, or hyperspectral imaging, mass spectrometry, NMR. It can be actually a great tool to help using these methods for more complex scenarios, because it's able to extract the data much better from, let's say, the noise, and it will enhance the performance of the existing methods. Now, the deep learning models, like for example, the convolutional neural networks, they are more suited for image spectroscopy-based analysis, for example, like near-infrared or hyperspectral imaging. And what is very promising is that they are able to recognize patterns in products, and they can look for anomalies. So if something changes in the supply chain, it's very easily detected and rapidly detected, and probably also guided towards where this comes from, certainly in combination with the Internet of Things. This is just an example where a deep learning model was used in combination with near-infrared. It also shows a bit of the limitations of the traditional machine learning models, which do have problems if they have to analyze these kind of complex data sets. But deep learning models seem to be quite well able, for example, in this case, declassification, to come to an analytical method that is able to do classification with an NIR, near-infrared spectroscopy. These are some more examples where deep learning is used in combination with NIR. For example, the identification of petroleum as an adulterant used to olive oil. It can be detected with near-infrared in combination with for example, deep learning model. It's more able to select the signal amongst the noise data, and it enhances the performance of the existing methods. Another example, the identification of brown mustard varieties, for example, also with the use of near-infrared in combination with a deep learning model. So that's one, I think, major application where we see more AI into food safety analysis, that it enhances the existing methods. I also looked a little bit of allergen testing, since that's one of the systems where which we test where we developed test kits for, and I looked for, okay, what is the status of AI in allergen detection? And well, it seems to be not so far yet. There is not so much applications on AI based for allergen detection. There was one publication that was about the FTIR, which was used in combination with machine learning, where they were made a model that they check the incoming goods and have an inline scanning method, and then look at let's say changes, and could identify to some extent, for example, weeds in buckwheat, I think it was. But although the specificity of this method is typically relatively high, sensitivity might be an issue. Certainly with the methods that were used at that time was machine learning application, and they also used the FTIR, which is not the most optimal tool if you're going to look at more heterogeneous products. So maybe hyperspectral imaging could be a solution to that. And also to use a deep learning models to come to a better sensitivity. But so far, the use of AI-based methods in allergen testing is very limited, but might change. Where it can help, for example, also mass spectrometry is also used in allergen analysis, but it generates typically also enormous amounts of data. And also, if you look at the mass spectra, they're highly complex. And again, I think AI could be also useful to, let's say, strengthen the performance of this kind of methods, to really isolate the peaks from the noise, and to have a better tool to identify allergen, also the ones we didn't expect, for example, that you can really run an untargeted analysis. And the AI will actually already tell you, hey, this could probably be this allergen you have in your product. For that, we would need really good open access of data. I think that is the crucial point. If you want to use AI and want to further develop AI, we need good data. And they must be accessible. And that's also the problem with the current models sometimes. They're based on a relatively small set of data and might not necessarily be that accurate as we think so. Here was also a study where they looked at different AI models and using, for example, NIR, hyperspectral imaging for different kind of foodstuffs in the field of food adulteration. Because, as I said earlier, AI is very good in detecting anomalies. Hey, if you scan a certain product over the course of time and suddenly you see something appearing, AI is very good in detecting that and also pointing in a direction where it might come from. There are some studies that are already published, and they typically show accuracies between, let's say, almost 100%. And in particular, in combination with hyperspectral imaging, those are very effective if you use them with, for example, deep learning models. I was talking now about hyperspectral imaging a couple of times, but I think that's really a way of analysis that works very well with AI. Those two are a perfect match together. That's a little bit about hyperspectral imaging. I don't know exactly if you know what it is, but it's a kind of imaging, of course. It's taking a picture. And instead that you have the information of every pixel where you have only red, yellow and blue, as you do for the visible eyes, we have for every pixel, we have a complete spectrum, depending on what you chose. If you choose for near infrared to visible, you can also choose from mid infrared to visible, but we have that for every pixel. So we have the combination here of spatial information, because we see this pixel, we have their complete profile of all the spectral data, which also means that the amount of data we have with this method is huge. And it's really, with, let's say, traditional method, it's not manageable. Which, hyperspectral imaging is not a relatively new method, but it was impossible to use before we could have, for example, machine learning and deep learning models to process this data. Now, this would be a really great tool, for example, if you scan incoming goods with an inline application. You take a hyperspectral imaging camera that looks at the incoming goods, and it will rapidly see if something is changing. and it will give you a method to come to an action to see from, hey, this is probably contaminated with, let's say, another commodity. And it is already used in some applications. For example, the classification of fruits. If there's spoiled fruits or grains, if there are broken kernels in there. For example, also looking at mycotoxins, cadmium in vegetables, adulteration of edible oil. There are certain applications already published. And I guess we will see more and more of this method in the future, where we see the combination of hyperspectral imaging and artificial intelligence. And that's really, as this publication also shows, those two are, let's say, more or less made for each other, because you have the spatial information and you have the spectral information for every sample. And that will give you, for example, the option, if you look at the freshness of fish, you can see, you can identify which kind of fish it is, because you can use AI to do the animal specification. You can also look at the freshness. You can see if there is bacterial contamination. And you might, for example, also see histamine based on the spectra which you have of every single pixel. Now, these data are so huge that you should maybe choose also to limit, let's say, the spectrum, that you take a certain part of the spectrum only to do this analysis. And of course, it does have the problems that you have to be careful that the calibration is really correct, and that the baseline you have in this system is really measuring what you're supposed to measure. But I guess we will see much more of these methods in the future. However, I think we'll probably see more easily beyond the use of artificial intelligence beyond analytics. AI offers a lot of other useful tools that will actually help us in the daily business for food safety management. For example, AI is already used in combination with the Internet of Things for many HACCP applications, HACCP-like systems. You could do, for example, supplier and product information on site and have quick QC check results. You could have early supply chain warnings. Also, if there is information available about problems with, for example, the harvest of certain commodities, those can be easily used in a data management system and draw conclusions from there. Safety alerts, recalls. Prediction of high-risk areas in production facilities. You can run and scan your production facility with an AI-based monitoring system, and it will give you an early warning if there is a problem cleaning efficiency. You could use inline spectroscopical data, for example, based on hyperspectral imaging or on computer vision. Process control data, hygiene monitoring. This can all be managed in one AI-based system, which will give you a real-time warning system. This is a recent publication where they developed a tool for the quality control of milk, where they also used the Internet of Things. So some of the basic measurements were in there, pH, for example, conductivity, temperature, in combination with spectroscopical data, which they used a kind of a near-infrared system for that, where they could then look for adulterants. And they used that in what was called an XAI, which is an explainable AI. And what I said earlier, the drawback of this deep learning models is that we have no clue what's happening there. It's the black box. And by an explainable AI, you have more insight in how this system actually came to the conclusions, which is more interesting because you can have, of course, better validate the system and also predict, for example, where there might be deviations. Now, this system described here was based on machine learning, and if you use indeed a deep learning model for that, it might even improve. And I think this is the first thing we'll see in the future, where AI will be used in food safety and food safety analysis, in supporting the analysis as well as in supporting us in the management of the quality control. Then if you look at the rapid alert system, I'll look here only at the allergen data. These are the data for about a year, 12 months. There were 98 warnings in the rapid alert system. And if you look at the major causes, most of them have to do with human error. And it's incorrect information on raw materials, errors in recipe management, errors in labeling, mixing up ingredients. Those are typical the human errors, not really the analytical things. Only the cross-contamination is an analytical thing where you can look at the analysis. And I think there is some serious room for improvement here. And if we would have an AI-based system, like these hazard-based systems, we might have really a great tool to make our food safer. So we're coming indeed towards what was mentioned in the earlier publication, toward a zero contamination, at least in the direction there. So where are we going? Well, I think AI already has influence on the food safety management. It will play a very strong role in pathogen detection. I didn't touch on that in my presentation, but there is a lot of publications and a lot of work already done on pathogen detection, prediction, and microbial risk assessment. Food traceability, supply chain monitoring, and early warning. I mean, food security is an issue. We have problems with, of course, due to trade problems, the wars going on. There might be issues with due to climate change and the quality of harvest. With a system like that, you get that early into your system also. When, hey, there's a shortage coming up for wheat, or there's a shortage coming up for buckwheat, for example. You have that in your system and it is flagged as a risk. Predictive modeling, of course, for contamination. I showed that earlier. Toxicology or allergenicity. Sometimes the question, is this substance, of course, toxic, or is this substance a new allergen? AI can actually help you predict the allergenicity, or can also help you predict toxicology. And there is a lot of publications on toxicology already available. Detection of food fraud. That is a very nice application where we will see more and more the use of AI, but also hyperspectral imaging, because it gives us now a better tool to quickly identify adulterations of products. Food safety analysis, of course, risk analysis and risk monitoring, preferably in real time, in a non-destructive way, would be great. Decision-making models, risk management models, market signals. I guess there was a lot coming. But we should keep in mind AI has a lot of limitations also. This is the Gartner hype cycle, which is typically, let's say, how hypes develop. We first go to the peak of big expectations. And once we say, it's probably not that, we go into the trough of disillusionments. And after that, it comes to maturity. I'm not exactly sure where we are with AI. I guess we're still on the way to the peak of inflated expectations. I mean, everything seems possible with AI, but there will be a point where say, that was probably not possible. But in the end, we will get to the real maturity of the market, and AI will be able to help us with food safety management. I mean, the predictive models are still in its infancy, also the use in analysis. We have to accept that. It's really based on data. Good quality data, because we know that AI can be influenced by bad data. I mean, I just heard in the radio that, for example, ChatGPT is influenced by data from, let's say, not so reliable sources. Until now, the acceptance by the industry is very limited, which has to do with the cost of instruments, also the cost of data generation. Deep learning models require really a significant computational power. It's not done on an easy system. You have to use quite some computational power. As said, the deep learning models, the black boxes, is a disadvantage, but by choosing for explainable AI, we might circumvent that. One example, which I used earlier this year and unfortunately is no longer valid, but if you asked the different generative AIs, make me a picture of a full glass of wine, and really full to the limit, you always get pictures like this. Very simple. All the AI models are trained on pictures in, let's say, stock agencies, and a glass of wine is never full. A glass of wine is always half full. So you can talk to the AI as much as possible. This is a full glass of wine. It just, based on the data, was trained on these data. It was also impossible to get half a glass of beer. You always got a full glass of beer, by the way. The funny thing is, ChatGPT learned, and all the generative AI learned from that. And it's now possible to generate a full glass of wine. So it is solvable, this kind of problems, but it is something we have to be aware of. These AI models are trained on the situation they actually see. And if those data were already biased, the AI will be biased as well. So that's something we have to keep in mind when we use these kind of systems. But besides that, I'm really convinced that AI will play a huge role in food safety management, and that can be indeed in testing and analytics, by enhancing the analytical methods, by maybe making new analysis possible, which we didn't focus on yet. It may support us on hazard-like processing, monitoring and alerts, and also for the prediction of risks. So yes, in the end, I would say the impact of AI on food safety is significant, but we should be aware of some of the pitfalls and use it to its full advantage. Thank you very much.